Hello and welcome everyone, this is Priyanka, and in this session we are going to talk about colligative properties. As in the previous session we have already discussed, colligative properties are the properties of solution which depend only on the number of solute particles present in the solution, and they are completely independent of the nature or composition of solute particles. We have studied that there are 4 colligative properties in total, which are relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. In the previous session, we have already discussed relative lowering of vapor pressure and the 2 laws based on it. In this session, we are going to particularly talk about the next 2 colligative properties, which are elevation of boiling point and depression in freezing point. So, let's start the first one. Elevation boiling point. Now, before talking about elevation of boiling point, let's first try and understand what the term boiling point means. Now, here in this picture, you can see a container filled with water. Now, boiling point in simplest term means that it is the temperature at which the vapor pressure of liquid becomes equal to vapor pressure of atmosphere. Now, that is for pure water is 100 degrees Celsius. As we all know, water boils at 100 degrees Celsius, that becomes the boiling point. So, what is happening is, once we provide enough energy to water particles, they are going to escape into vapor phase. Now, let's try and understand what happens when we add some solute particle in this pure solvent. When we add some solute particles in this pure solvent, what will happen is the solute particles are going to try and react with the solvent particles present in the solution, and which is why it will be more difficult for our solvent particles to get converted into vapor phase. And for that, we'll have to provide some more heat to convert them into vapor phase, which is why there is elevation of boiling point. So, the boiling point for pure solvent, in this case we have considered water, is 100 degrees Celsius. When we add some non-volatile, non-electrolytic solute, the boiling point is supposed to be higher than 100 degrees Celsius because of the difficulty of solvent particles to get converted into vapor phase. Now, elevation of boiling point is basically temperature difference of boiling point of a solution and that of a pure solvent, which is represented as delta TB. Now, that suffix B means boiling point. Now, as you can see, delta TB, which means that TB minus T naught B. Now, that is experimentally found to be directly proportional to molality, which is represented by letter small m. Now, if I want to remove the proportionality sign, I can put a proportionality constant. In this case, we'll call it as Kb. Now, we get the equation as delta Tb is equal to Kb multiplied by m. Here you must note that Kb is called as ebullioscopic constant or molal elevation constant. Now, as you all know that m, which is molality, has a unit of mole per kilogram. Now, we know that molality can also be represented symbolically as W2 divided by M2 multiplied by W1. And hence, the entire formula can be summarized as delta Tb equal to Kb multiplied by W2 divided by M2 multiplied by W1. Now, if you want to study this graphically, we've taken temperature on the x-axis and we've taken vapor pressure of the solution and solvent on the y-axis. So, as you can see, there are 2 curves present in this graph. One is for the solvent and the other one is for the solution. Now, what is happening is, if you notice the first curve in the graph, which is for the solvent, that is meeting the 760 millimeter mark at temperature T naught B. That means, at temperature T naught B, the vapor pressure of liquid becomes equal to 1 atmospheric pressure, which is your 1 bar. Now, what happens when you add some solute and make a solution out of it? Now, you can see for the solution curve, the temperature has to be raised and that is equal to Tb, and at temperature Tb, which is greater than T naught B, the vapor pressure of liquid is going to be equal to 760 millimeter, which is 1 atmospheric pressure. Now, let's have a look at the third colligative property, which is depression in freezing point. Now, before talking about depression in freezing point, let's first try and understand what the term freezing point means. Freezing point in the simplest term is the temperature at which solid and liquid coexist, or simply liquid starts getting converted into solid state. Now, as you can see in this picture, that we have pure water, and for pure water, freezing point is 0 degrees Celsius, as we all know. Now, let's try and understand when we add some solute into it, what changes do take place. Now, when we add some solute, the liquid particles have to put even little more efforts to get coagulated or to get converted into solid form, which is a more structured form. And that's why when we add solute in the solvent, the temperature has to be lowered than 0 degrees Celsius to get converted into the solid form, that is to get freezed. Now, experimentally it is found that the depression in freezing point, which is the temperature difference between the freezing point of pure solvent and freezing point of solution, is directly proportional to molality, which is small m. Now, if I want to remove the proportionality sign, I am again going to put a proportionality constant. In this case, that is called as Kf. Now, you must note that Kf is also called as cryoscopic constant or molar depression constant. We have delta Tf, that F represents the freezing point. Delta Tf equal to Kf multiplied by m. Now, m, as we all know, is molality, which is measured in mole per kilogram. Now, which is symbolically represented as W2 divided by M2 multiplied by W1, and the entire equation can be summarized as delta Tf, which is depression in freezing point, is equal to Kf multiplied by W2 divided by M2 multiplied by W1. Again, we are going to study this phenomenon graphically. Let's just revise what are our terms. Tf is the freezing point of solution. T0F is the freezing point of pure solvent. Now, let's study this graph. On x-axis, you can see we've taken temperature, and on y-axis, we have vapor pressure. Now, you can see that there are three curves present in this graph. The first curve that I want you to focus on is the solid solvent curve, which is present on the lowest part of the graph. Then there are two other curves which are present in the graph. One is liquid solvent and the other one is solution. I want you to focus on the two curves which are liquid solvent and solid solvent. So, when liquid solvent gets converted into solid solvent, the temperature is called as T0F, which is the freezing point of pure solvent. Now, what happens when we are adding some solute? I want you to focus on the two other curves that we have. I want you to focus on the curve which is solution and the other curve which is solid solvent. If you see, for solution and the solid solvent, they are meeting at a point which is on x-axis called as Tf, which is definitely lower than T0F. And that's why we can conclude that when we add a solute in the solvent, the temperature, which is the freezing point, is lowered as compared to the pure solvent. With this, we've covered the two colligative properties, which are elevation of boiling point and depression in freezing point. I hope you found this video useful. If you did, please hit the like button and subscribe to our channel. Thank you.